We were looking yesterday at this the basic structure of the nucleus, and that is that the nucleus has neutrons and protons. The neutrons have this mass here, 1.675 by 10 to the minus 27 kilos. Protons are positively charged and have this mass here, 1.673 by 10 to the minus 27 kilos. Very small difference between those two. The mass of the electrons is much smaller. The atom itself is a whole lot of nothing. If these particles here were the size of a fly, then the electrons, the first electron shell would be out at the edge of a stadium, as if the fly were in the center of the field in a stadium. Okay, so there's a whole lot of nothing in here. The electrons are 1840 times less massive than the protons and neutrons. Collectively, they're called nucleons. And the question that I asked was that if there's protons and there's positive charge in the center, how is it that this nucleus stays together? Well, there's this thing called the strong force. It's the strongest known force. Why doesn't the nucleus fly apart? Strongest known force, very short range, works over only a few nucleon diameters, so doesn't work very far. Okay? At very short distances, nucleons are attracted to each other. At extremely short distances, so this is a bit of a qualitative view of distance. Very short distances attractive, extremely short distances they repel each other. This makes sure that that the nucleons themselves, the protons and the neutrons, remain independent of each other. They're not just one solid mass in the center there. Lucky for us, if that wasn't true, then we wouldn't be here. We wouldn't be talking about physics. The force is independent of the type of nucleon. So the strong force, it doesn't matter whether it's a proton or a neutron, the force is exactly the same. The strong force is the same for both of those. This diagram here just shows, what happens when we fire an alpha particle at reasonably low speed, relatively low speed at this nucleus. It tends to just be deflected because this electrostatic force, the positive charge of that nucleus works over a very large distance, arguably to infinity. And so this positive charge here on this alpha particle is repelled by that. And the alpha particle doesn't get anywhere near that nucleus. In some situations, we can get nuclei to actually be accepted. If we can get them close enough that that strong force overcomes that electrostatic repulsive force, then the nucleus may or may not accept that nucleon. And then what it does is, it depends on what it is. Sometimes the nucleus can kind of break into two pieces. Sometimes it can throw off another particle. It can do several things. Okay, so that's the strong force, strongest known force. Have I skipped a bit here? Hang on. No, I haven't. Okay. Isotopes. What is an isotope? Does anybody know? The chemists in here should know. Yeah, different. Yeah, essentially it's an atom or an element. Okay, so we might say this. You got something there you want to add, Jacob? Oh, I've just drawn two of exactly the same isotope. Oh, one thing I didn't note, and this is important. Oh, did I talk about this? This A equals what? Mass number? No, I didn't. I better say this. Z, atomic number. And in the equation that I'm about to put here is the number of neutrons. A equals Z plus N. And some notation. If X is the symbol, chemical symbol, then I write this. I write the mass number here, A, and the atomic number here. Most people will know this already. As an example, 5626 iron. I think that one's correct. I haven't got it here. Does anybody confirm that iron is atomic number 26? I think that's right. And so what this says is it has 26 protons in its nucleus, and it has 56 minus 26 neutrons in its nucleus. And we call it iron. That's just the common name that we give to it. You could actually just say, really, you could just say iron 56. Because if it's iron, we know it has 26 protons in its nucleus. 56 denotes something else. Because there might be other ions, and I know there is. A different number that I put at the top here for A. And that's when we look at isotopes. Here's some isotopes of oxygen. Number of protons, number of nucleons. I can see that that has 6 neutrons in it. This one has 7. This one has 8. This one has 9. This one has 10 neutrons. And this one has 11 neutrons in its nucleus. What do you think is different about those things? Number of neutrons in the nucleus, absolutely. Straight away, you can see that. What do you think is different when I make, for instance, I have a free oxygen molecule and I have another free oxygen or atom, 2 oxygen atoms, and they come together to form O2. I think it's got 2 bonds, chemists. Is that right? Is that how you draw O2? Thank you. And so what if this was oxygen 14 instead of oxygen 16, for instance? How is that going to react differently to, say, if I breathe it in? What's going to happen to me? There's something wrong with that oxygen as far as my body is concerned. I kind of gave you a hint by the way I asked it, didn't I? Not really, no. My body takes that in, because what sort of reactions go on inside all of our bodies? Not nuclear reactions. Chemical reactions, okay? Yeah, respiration is a chemical reaction. Now, so as far as my body is concerned, this is just oxygen, O2, the diatomic molecule oxygen. And it hasn't got a problem with it. Except this oxygen itself might be a little bit dangerous. How? Radioactive, yeah. I don't know that oxygen 14 is. It probably is pretty unstable though. And likely not to stay in that form. I don't even know whether it's stable enough to form this O2 molecule. But if it is, and I breathe some in, my body would just say, yeah, no worries, that's oxygen. And you would keep breathing. Everything would be fine, except you'd have some oxygen running around in your blood that was potentially radioactive and probably could emit particles. And that's not necessarily good for you. But there is an application to these things. Does anybody know what the application is? Medical imaging. If I, here's me, and not oxygen, but fluorine's one. If I take in some fluorine, my body uses fluorine in a certain way. When I eat something or breathe something in, or drink something or consume something or otherwise allow something into my body that has some fluorine in it, my body uses that fluorine in a very specific way. It sends it to certain places where I metabolize that fluorine or use it in metabolism, and and uh, and so because of that, if I send in fluorine that's an isotope of fluorine that happens to be radioactive, then and it sends it to, say, my thyroid gland. Okay, what happens is my thyroid gland very specifically starts giving off radiation. Just my thyroid gland, okay, or certain glands in the body. And if I then image that and 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 count the radioactive emanations that are coming off, I can take a photograph or I can take a picture of what my thyroid gland looks like. This is helpful because certain cancers and certain organs like certain chemicals. And if I make that chemical an isotope of the chemical that is radioactive, then I might be able to use that in medical imaging. Therefore, without any invasive surgery, the doctors can have a look and see, oh yeah, that thyroid looks all right, looks like it's the right shape, doesn't look like anything's wrong, without opening me up and causing my body trauma. Okay, so it's good for, and it's a lot cheaper, of course. You don't need an anesthesiologist and an anaesthetist. You don't need any of the many people that are involved in looking after you when they cut you open. Okay, it's just a trip to the doctor essentially, or the hospital. So that's why we're particularly interested in isotopes. Isotopes are chemically identical. By identical, I mean exactly the same. Okay. This this stuff here, oxygen 819, we call it oxygen. This is if you're at a party and you want to talk about oxygen 19, that's what you say. Oxygen 19. That's the way to say it. All right. If you're at a party, don't be talking about oxygen 19. Nobody's really interested. Now, okay, mass defect. And binding energy. Does anybody know what these things are already? What do you think we might be talking about when we talk about binding energy? Considering what I've just been talking about. Yeah, energy that binds the atom together, or specifically energy that binds the nucleus together, which makes up most of the atom, most of the mass of the atom. Yes. So this isn't. You can't have a proton and a neutron and a neutron and a proton floating around in space, and they just coalesce. They just come together. It doesn't happen like that. There's some energy associated with the bind there. And I'll show you, what is this stuff? Helium. You're sharp today, people. Helium-4, we'll call it now. We'll be more specific now. Helium-4, and this is a neutron, and this is a neutron, and this is a proton, and this is a proton. Proton might be written like this. Neutrons might be written like this. Something interesting about this. The mass of this thing, mass of the helium nucleus, M sub He, equals 6.64489 by 10 to the minus 27 kilograms. What do you think if I add these masses together, these equal? Different, yes. It's not the same. It's a little bit more. Yeah. It was good. It was good that he said that they were going to be different, for starters. There's a binding energy associated with that. Now, I'm talking about mass and energy. What can you see straight away? What do you think? So the mass of these nucleons, I'll call it. What do you think Einstein thought of this straight away? Yes. What's that? Mass and energy are equivalent. Yeah, so he said this. Mathematically, he said mass, energy equals mass multiplied by a really big number. Okay? Mass and energy are one and the same. It's a way that we can look at it anyway. Mass equals energy, essentially. Is that what that says? It means that if I want to make this out of these, what do I have to do? Put it, take. Yeah, that's right. Yeah. So in our experience, what do we have to do? We have to fire these things at each other until they kind of, the strong force takes over. And so they need energy to do that, don't they? But when they get close enough, if you just look at their masses, this thing here, or these things here added up together, have just slightly larger mass than this here, right? So what happens is when I bring these together, I have some spare energy. Energy is released in that reaction, in that nuclear reaction, in bringing those nucleons together. This is useful. Yes. Without the stars, we wouldn't be here either. Let's actually do the calculation on how what that is. Mass defect is this, we call it delta M, change in mass, is this energy. And we calculate it by taking this number, 6.69534 minus 6.64489 by 10 to the minus 27 kilograms. We're left with 5.045 by 10 to the power of minus 29 kilograms. Unaccounted for. Has gone somewhere. It's become energy. We can use Einstein's equation and find out what that energy is worth. 5.045 by 10 to the minus 29 kilograms multiplied by c squared .5405 by 10 to the minus 12 joules, of course, is our unit for energy. That's some energy. We don't, when we're talking about small energies, we don't like to talk in joules because joules is a large unit, so we change it to EV. Can anybody remember what I do? Yes. Divided by 1.6. by 10 to the minus 19 coulombs. EV, 2.8378 by 10 to the power of 7 electron volts. That's a nicer number because I can call that equivalently 28.4 million electron volts, mega electron volts, MeV. And there's a reasonable number for physicists to talk about when they're talking about the energy change here, or the energy change in that nuclear reaction. We'll define the binding energy. Binding energy. Has anybody got an idea about what how you would define the binding energy? That's it there. Is the energy required to split a nucleus into its constituent nucleons? I have to supply energy to this nucleus to break it up. Doesn't seem fair. And equally, in our eyes, I have to supply energy to get it to stick together because I have to bring them up to very high speed. But when they get very close to each other, it doesn't require any energy. That's it gives off energy. If I can get a chain reaction to happen, so I can yes, speed up some particles to make them bind together, and then that reaction to continue on without me adding any more energy because there's lots of atoms around, then essentially I have some free energy, don't I? Because what have I done by doing this? What have I done by bringing particularly these two things together? How much energy is required to bring those two things together? That positive charge and that positive charge. Well, you can just give me a qualitative number. Lots of energy. So much energy that we find it difficult to do on the surface of this planet. And in fact, it only goes on in stars, really. We call it fusion. We need high pressure and high temperature. So we need those particles. Temperature is just the speed of these particles, essentially, the kinetic energy of the particles. And so I need high kinetic energy. I need high pressure, talking about the pressure that is involved in the density of the sun. And we have fusion taking place. Lucky for us, if the sun wasn't there, we wouldn't last very long. Some laws. Conservation laws. Number one. Conservation of charge if I have a nuclear reaction, now here's an example. Helium plus some nitrogen reacts. Now we're not talking chemical reaction now, we're talking nuclear reaction to form 17,8 oxygen plus, what is it going to be? Put in 4, 7, 1 as 9 and 1 proton, or a hydrogen nucleus. Conservation of charge says that the total number of protons on this side is equal to the total number of protons on this side. And the protons are the only things with charge at this point that we're looking at. Okay? So 9 protons versus 9 protons. The chemists will know that you have to balance both sides of the equation. The mathematicians will know that you have to balance both sides of the equation because they are equal. Okay. Number 2. Conservation of nucleon number. What do you think that one means? Yeah, what specifically is the same for both sides? Nucleus? Some of the protons are neutrons. So I've got 18 nucleons here on this side of this equation, and I've got 18 here. You guys are going to find this easy. 14 plus 4 is 18. Are you sure, Abby? Yeah. And 17 plus 1 is 18. You paused. That's good. So these numbers have to add up to these, and these numbers have to add up to equal the same thing, and so do the bottom numbers. Bottom numbers have to equal the bottom numbers, and the top numbers have to equal the top numbers. I could have said it that way. But if you are asked that as a conceptual idea, you need to be able to say it in physics terms. Conservation of momentum. Of course. What does that mean? Yeah, that's right. Before the momentum on this side of the equation is equal to the momentum on this side of the equation. So this is kind of the before, isn't it? P before is equal to P after. Okay, yes, that's true. And it says that the total momentum of these two nuclei is equal to the total momentum of these two nuclei. For conservation of energy, of mass energy. Now, we just did a calculation before where we broke up a helium nucleus and we broke up a helium nucleus into its constituent nucleons, and we noticed that in doing so, there was a change in energy. Now, the energy, the binding energy, and the energy of the nucleons on this side must be equal to the energy of the nucleons on this side. Energy is conserved. You don't get anything for free. Again. How do we get power from fusion? Or fission, yeah. We can get power from fusion, but we have to put more power in than we get out at this stage. If I have enough atoms, and I get one atom to, it's all to do with kinetic energies of molecules, and it's all to do with the chain reaction. That energy is locked up in the binding power of those nuclei. So you've heard the idea that a kilogram of seawater could run your car for 12 months or something like that, okay? Everyone's heard that, haven't they? I thought, how do we do that? I'm sick of putting petrol in my car. It's expensive. Well, it's really hard because the nuclei that make up that water are numerous, obviously. There's lots and lots and lots of them. And the thing that hold those nuclei together is energy or mass. And if we could just get that mass out, then that kilogram of seawater has huge amounts of energy contained within it. So it's all locked up in there, but we just can't get it out efficiently at this stage. So it's kind of already there. We're not making something for nothing. Okay? We're just converting it, yeah. That's right. Can't create or destroy energy. Some balancing. So let's try some balancing nuclear equations. See if you can balance this. Beryllium 9 plus a proton reacts to form this Is it too late in the day on Friday? 4 plus 1 is 5. 2 plus 3 is 5. 9 plus 1 is 10. 4 plus 6 is 10. Easy. No? That's all right. You can do the next one. Okay. 23892 uranium. Something happens to it. A nuclear reaction of some sort. We end up with kryptonite. No. Thorium plus. What do you think it is? It is helium. Helium. And you would, so here, yeah, that's right. Look, have a look. 92, 90, we need another 2 here. So then it's automatically helium. And 238, I need to add 4. Yes, that's good. Helium. Easy. Have I got enough room? No, I haven't. If the mass of the reactants is greater, everybody knows what reactants and products are, don't they? Is there anybody that doesn't know what reactant is and what a product is when we're talking about reactions, chemical or physical? Nuclear, sorry. Greater than the mass of the products. So reactants. Reactants. Products. Matter has been converted into energy. Or energy is released. If the mass of the, this is probably pointless, I could just say, and vice versa, reactants is less than the mass of the products, matter has been created. That's a good way to say it. And energy was required. Energy is absorbed, you could say. Somebody said in the other class, energy absorbed. What's that? Yeah, endothermic. Yeah, that's right. Now that when we talk endothermic for a nuclear reaction, I guess applies as well. Yeah. Yes. Very good. Exothermic, endothermic. See if you can do this one. What's this stuff here that I've just drawn? Plus. What's this stuff here? It is a hydrogen isotope, isn't it? Yes. It's called deuterium. Mass of reactants equals 2.659 by 10 to the minus 26 kilograms. Mass of the products, M sub P, 2.656 by 10 to the minus 26 kilograms. Tell me what happens. Tell me about the energy. Calculate for me the energy required in EV, and tell me whether it's required or whether I need to. I'll get some energy out. One of the two. Mass defect 2.659 minus 2.656. You guys are going to have to tell me if I get this right by 10 to the minus 26, or tell me if you got it right, because we did the calculation before. Yes. So it comes out at 0.03 by 10 to the minus 26, of course, which is 3 by 10 to the power of minus 29. That's scientific notation, yes. Then you put it into Einstein's equation, E equals delta mc squared equals delta m. Mass defect is 3 by 10 to the minus 29 times 9 by 10 to the 16, which equals, shortcut here, 16.8 MeV. We would have got 1.68 by 10 to the 7 EV would have been the number. Is that energy released or absorbed? You guessing? Mass of the reactants is greater than the mass of the products. Energy is released. Thank you. Very good. Any questions about those calculations there? They're reasonably straightforward, aren't they? Yeah. Good. Kinetic energy. This is a nucleus. We call it the parent nucleus. Daughter nucleus. Now this is before reaction, and this is after reaction. So just a little bit of lingo here. Daughter nucleus, and this might be a particle. Whatever particle has been emitted by the parent nucleus. Momentum is conserved, so that's a velocity, and this is a mass. This is a velocity, and this is a mass, V2, M2. We like to think of the parent nucleus as starting off with a momentum of 0. It's not moving. It's just sitting stationary. And then it throws off a particle, whatever this particle may be. Because it throws off that particle, it must go in the opposite direction very slightly. But the total momentum of that system must be 0 afterwards also. Momentum is conserved. Okay. We'll call this P sub P and this P sub D. But the P sub D includes the daughter nucleus, and this is P after, maybe. After. Momentum after. This is okay, so P sub P is equal to P after. Momentum is before is equal to the momentum after. Oh, hang on. Sorry. Go back. I'm not comparing these two. I'm comparing these two. I forgot that that's what I was doing. I only did it before. This is the daughter nucleus, PD plus P of the particle is equal to 0. But this is kind of like because this is going in the opposite direction, we might say that. Okay? Yeah, that's right. So PD minus P of the particle, momentum of the daughter nucleus minus momentum of the particle is equal to 0. And from that you can get this. P of the daughter, momentum of the daughter nucleus is equal to the momentum of the particle, M1, V1, that's what I call them, yes, is equal to M2, V2, momenta are the same, M1 on M2 is equal to V2 on V1. What does that mean? The ratio of the masses, hang on, the tablet's slowed down for some reason, masses is in inverse proportion to the ratio. What does this mean? Ratio of the velocities. Yeah, well, if the mass is really large, then the velocity is small. And if the mass is really small, then the velocity is large. You already knew that. I just said it with some maths and some funny lingo. But you might have to describe that one day, okay? Easy enough. Kinetic energies. The kinetic energy of this particle in relation to the kinetic energy of this particle, or the ratio of the two. So if this is our alpha particle and this is our daughter nucleus, so imagine it's an alpha particle, for instance, okay? What sort of number are we going to get, do you think? Is this bottom number going to be smaller than the top number and so we have a large positive number? Or is the bottom number going to be larger than the top number? And therefore we're going to have a small number. Small number? So the kinetic energy, what you're saying by saying that is that the kinetic energy of the daughter nucleus, the larger of the two particles, is larger than the kinetic energy of this little particle. Have a look. Okay, yeah, I didn't say it very well, Matthew. It's not because you didn't understand it. Okay, let's just move through and do the maths with it, and it might be obvious. M2 V2 squared over M1 V1 squared. Okay, I'll break it up again. M2 over M1 V2 over V1 squared. But I can change this to something more usable that we did before. from this, I can say this, but M1 on M2 equals V2 on V1. So, okay, so from that, we can go equals M2 on M1. Oh. M2 on M1 times M1 on M2 squared equals M1 on M2. Which, remember, equals K2 over K1. The kinetic energies are in inverse proportion to the masses. Are in inverse proportion to the masses. So let's imagine that this is thorium. These are the numbers I've got, and this is an alpha particle. Let's look at the mass numbers. Kinetic energy, or mass of thorium, mth over m alpha, is equal to 234 on 4, which equals 58.5. Kinetic energy of the alpha particle is going to be much larger. The kinetic energy of alpha is much larger. I'll leave it at that.